Hello and welcome to day 14 of our video journey to ace the interview. Let's begin our daily question. Question 974, subarray sums divisible by k. Given an integer array nums and an integer k, return the number of non-empty subarrays that have a sum divisible by k. The subarray is a contiguous part of arrays. For anyone that doesn't know, contiguous means that it doesn't skip any elements between the start and the end. So, for example, in a contiguous array, subarray of nums would be from one index to the other without skipping any intermediate index. Let's look at some examples now. The total number of subarrays of this nums array, the sum of which is divisible by 5. Divisible meaning that the remainder is 0. And the examples are the whole array itself, 5 modulo 5 equals 0. The sum of this is also 5, so 5 modulo 5 is 0. 5, 0, negative 2, negative 5, sum of which is 0, modulo 5 is 0. Same goes for this, same goes for this, same goes for this. Sounds good. To solve this kind of question, you need to know of an algorithm that I'm gonna show you in a second, but before that, let's construct a array of length nums that's going to hold the sum from index 0 up until that number that we're exploring currently, modulo k. So let's call it remainders. Let's initialize sum to 0 and say for num in nums, s equals num, and remainders append s modulo k. Let's print and see what this looks like. I'll explain why we're doing this in a second. As you can see here, 4 modulo 5 is 4, 9 modulo 5 is 4, 9 modulo 5 is also 4, 7 modulo 5 is 2, 4 modulo 5 is 4, and 5 modulo, sorry, this was 6. This was 9 modulo 5 is 4, 6 modulo 5 is 4, and 5 modulo 5 is 0. And that's what you see the result. That's what you see here. Now, I'm going to make a claim that you guys should process probably on your own, because it's going to take a while to understand, but as I'm traversing this array, if I encounter a subarray whose remainder is equal to my remainder, for example, let's say that I've only processed these two values so far in the next for loop that I'm about to write, and I'm on my third value. If my remainder happens to be the same as some previous remainders, then that means that I've just generated 2 more subarrays whose sum is equal to, whose sum's modulo is equal to 0. The way that I would explain this visually would be something like this. I have an array of values. Let's say that now let me try to visually explain what this array actually means. This is equal to sum of num 0 modulo k, this value. This value is equal to sum nums 0 plus nums 1 modulo k, and so on. I've set the pattern. Let's look at the final example of a pattern. Let's pretend that we're exploring index 4. Zero plus nums 4 modulo k. What we can notice here is that if this value is equal to, in our example, let's say that it is equal to 4, and the 2's value is also equal to 4, then the difference, so that means that this subarray's sum is going to be equal to, this subarray's sum, when taken the modulo of, will be equal to 0. There is a pretty good proof to show this. For the purpose of saving time, I'm going to let that be explored on your own. But I assure you that if you are already aware with the algorithm, then seeing this explanation would probably make more sense. Let's implement the rest of this function to actually keep track of how many remainders of the same kind I have, such that when another remainder of the same kind appears, I can make the right, I can add to the result the right amount, because it's not always going to be, let me explain this also, that if the first subarray's result is 4, the second subarray's result is 4, then we're adding 1, however, to the result. However, when we hit the third, and there already exists 2 subarray's results that are equal to 4, we will be adding 2 instead of 1. Similarly, in this case, there already exists 3 subarrays of this count, which means that when we're in this value, there's going to be 1 subarray whose remainder is equal to 0, 2 subarrays, and I'm similarly highlighting it here, and 3 subarrays. So you are essentially adding 3 to the value, to the result. Let's call module mode array of length. I'm going to say remainder array, remainder sum. Just going to be equal to 0 times k. And now I'm going to say for remainder in remainders, I'm going to say that result is plus equal to the remainder array, remainder sum rem. And finally, I'm going to add that I have just encountered another remainder of that value in my array and return res. Let's see if this works. Okay, we have a output that doesn't work. It's saying that the output should be the output is 6. However, the expected value is 5. And I think that if we're off by 1, and this doesn't, yeah, if we're off, okay, so yeah, if we're off by 1, then there's a good chance that I messed this up. You can notice that if we encounter in our remainders array an array whose a subarray whose remainder is 0, that means that it is immediately equally or fully divisible by k without a remainder. So we have to set the initial value of the 0th remainder to 1. Let's run this, see if this works. And awesome, we are in the 98th percentile. Yep, I'm making a quick, there is another solution to this that doesn't involve making the remainders array that I can quickly share with you at the expense of memory. Let's go through that a little bit. The reality is we don't need this remainders array at all, because we could calculate the sum on the fly. Let me show you how that would be done. If we have something called the prefix sum equal to 0, then we could essentially say that prefix sum is prefix sum. So we're getting rid of that num remainder num remainder modulo k and initialize the remainder to 0. Remainder sum is not actually a thing yet. Index out of range. Oh, index out of range. This is probably because we're hitting a negative. rem. Let me see. Nope, we're not hitting a negative. We are just let's rename this for we're not plus k. Sorry, 1 second. What I'm trying to do is basically keep a constant. Keep the array that I had here as an ongoing sum called the remainder. Let's call it the remainder sum to make it more obvious what it is. The remainder sum is equal to the num plus the remainder sum is equal to, I'm not adding, let's say num modulo k, num modulo k, and let me see, expected 3. At any point, am I getting a rem sum that is negative? Nope, I am not. So I'm getting, what am I doing wrong? Plus k. Modulo k. Okay. Yeah, this is at the expense of some memory, but what this is doing is keeping a track of the remainder array that we have here as we are as we're traversing this array in the form of rem sum. Okay. Hopefully this is a short video and I have two pretty good solutions. The latter, this one, is a little bit harder to understand, so this one is a lot more intuitive for me, and it sort of dissects the problem into two separate problems. First, understanding the pattern that I was talking about here, that a subarray's module equaling, or the subarray's remainder, the subarray's sum remainder can be used with other subarray sum remainders to figure out different to figure out essentially that the difference between those two subarrays will be the remainder of that will be equal to k. And since we don't care where those subarrays actually are, comes the second portion of the problem, which is figuring out that we can keep track of how many subarrays sum's remainder is equal to some number in a variable called remainder sum, which gives us blazingly fast response times. I think it's even putting us somewhere close to the top 100. But anyway, yep, thanks for watching, and I'll see you next time.